Today our lesson is on the nature of light. So we've talked about electricity and electric fields, and we need to talk about what happens in a special case when a charge is moved. So here's a little applet which will help us kind of figure out what's going on. Suppose I put a charge over here on the left. Now we can draw a picture representation of what this charge does to the space around it. And we call this picture an electric field. So the electric field kind of shows what would happen um, or how this charge would sort of distort space in its neighborhood. So if I had a little tiny positive charge right here, because of this charge over here would feel a force to the right. And so if I put my little test charge over here, it would feel a force downwards. If I put it right here, it would feel a really big force down to the right. So what the electric field is showing us is the force that particles would feel at that location. So on this charge right here, this little test charge, there's a force to the right. Now, if I grab this charge and I moved it up, the field changes. And you can notice that over here on this test charge, the field is now pointing down and to the right. And if I move this down, the force over here will be pointing up. So that if I took this charge and I wiggled it up and down, then you can see that this little charge over here feels that force changing directions. What you can actually see is the electric field, the distortion caused by this charge right here. It actually wiggles. It's like a disturbance that's propagating outwards. And that's exactly our definition of a wave. It's a disturbance that propagates. So if we were to take a charge and put it in an antenna and shake it up and down, that would cause a propagation in this electric field, which could be felt by another charge over here. So we could communicate with charges in this antenna by wiggling the charges in this antenna up and down. And so we call that an electromagnetic wave. The disturbance that travels outwards in the electric field also travels outwards in the magnetic field, which we haven't covered yet. And that's called an electromagnetic disturbance or an electromagnetic wave. So when you have a charge vibrating or accelerating actually, it produces a disturbance in this electromagnetic field, and that disturbance propagates outwards. So over here you're perhaps shaking a charge, and this kind of shows the disturbance of the electric field as it travels outwards. You don't really need to understand the details of that too much. What the important point is that a accelerating or a vibrating charge produces disturbances which travel outwards, and those are called electromagnetic waves. Now it turns out us humans and most animals have detectors for these waves, amazingly enough. We can measure and we can sense these really small changes in the electromagnetic fields. And those detectors are called your eye. Your eye is an amazing electromagnetic wave detector. There are some very complicated proteins which have molecules which can detect very small changes in the electric field because they have some bare charges that can sense those. And so when there is a wiggle in the electromagnetic field, like some electrons are wiggling back and forth at really high speed in a light bulb, they send out a disturbance and your eye can detect that. Now, how fast do these disturbances move? Well, for most of time, people thought these disturbances moved instantaneously. That is to say, if you turned on a light, that light spread out in all directions instantaneously. Galileo was the first one who thought, or seriously thought, that maybe it wasn't instantaneous. Maybe it was just really fast, faster than you could normally notice. So what he did was an experiment where he had an assistant stand on a distant hill over here. And so we're talking a couple miles apart here. And he had a lantern and he had it shuttered. And he would uncover his lantern and the light would travel across until the guy on the other hill could see a little speck of light. And as soon as he saw a speck of light, he would unshutter his lantern, and that would send some light back. And Galileo tried to measure how long it took the light to travel across to the other mountain and back. The problem was the time he was observing was pretty close to the reaction time of humans. And so there was a huge amount of uncertainty, and his measurements weren't very good. And given the uncertainty of the reaction time of humans, he couldn't tell whether light traveled instantaneously or not. But at least it was a good idea that maybe light doesn't travel instantly. So some clever experiments were done over the course of the next couple hundred years. Rohmer, who was a Danish astronomer, was doing some very accurate calculations of the eclipses of Jupiter. So when the moons of Jupiter go behind Jupiter and you can no longer see it. And he noticed that when the sun was between Earth and Jupiter, the time it took the moon to go around Jupiter seemed shorter than when he was over here. And so he basically was able to do a clever experiment where he figured out how much longer it took the light to travel to the Earth when it was on the opposite side of the sun. And so using the radius of the sun's orbit, he was able to get a rough estimate. There's a clever little animation you can watch. It's not that important for our purposes, but it's interesting how this was done. You can look up Rohmer speed of light experiments, and there's some nice animations that kind of fill you on the details of that. So a lot of physicists have spent a lot of time trying to accurately measure the speed of light. Fizeau was a French scientist who measured it by a rotating strobe disk that he shone a light through. So what we now know is that the speed of light travels incredibly fast, and it turns out that we know it really, really accurately. We've done so many experiments and made such careful measurements. We know the speed of light is 299,792,458 meters per second. That is 9 significant figures of precision. That is absolutely amazing. To give you a kind of way to wrap your head around that, that's about 186,000 miles in 1 second. So the light can just travel really fast. So for our purposes, that's instantaneous. But that speed is well known. In fact, it's so well known, we actually define the length of a meter based on how far light can travel now. So in the old days, a meter was thought to be, the people in Paris wanted to make the meter 1/1,000,000th of the distance from the North Pole to the equator on a line that passed through Paris, France. That became really hard to use, and so they found a stick, brass, and they said, hey, that's 1 meter. But the problem was it kept changing when it got hot and cold. So they kept another piece of metal, platinum, at a constant temperature using ice, and they said that's 1 meter. And nowadays, we just measure a meter based on how far light travels in this much time. So we can do these very accurately now, and the meter is now actually defined on the speed of light. So light doesn't have any measurable acceleration, and so when light is turned on, the waves propagate outwards, and they propagate outwards at 3.0 times 10 to the 8th meters per second. And so if you want to know how far they go, it's very easy. So this is like back in August equations, right? The distance the light goes is equal to its velocity times its time, and its velocity is always the same in a vacuum. It's 3.0 times 10 to the 8th. So to solve problems, we're going to use distance equals rate times time, and the rate, the velocity, in meters per second is always 3.00 times 10 to the 8th meters per second. The actual value, you may remember, was 299,792, but if you use 3 significant figures, that's 3.00 times 10 to the 8th. So we're going to solve some fairly simple problems with this assignment to just get an idea of how fast light travels and how far it can travel in various amounts of time. So here's an example of a problem to solve. Voyager was launched in 1977. It made several spectacular flybys of the outer planets, starting with Mars, and then Jupiter, Saturn, and so forth. And it is now way out past Pluto and it is in what we call interstellar space. It's sort of left our solar system, and it's 11 billion miles from Earth. So what we want to know is, how long does it take a radio signal, or a light, an electromagnetic wave, to go from Voyager all the way back to Earth? Because Voyager is still communicating with Earth and still sending back data. Um, it's not going to last too much longer because its little power plant is running out of energy and it's too far from the sun to use any solar panels. But how long does it take? So here's what we know. We know the distance from Voyager to the Earth is 11 billion miles. And remember, billion is 10 to the ninth. And that's in miles, so we're probably going to have to convert that to meters because our velocity is in meters per second. So first thing we're going to do is convert the distance to meters. We know there's 1,609 meters in a mile, and since we're starting with miles, we need this in the bottom. So that's going to do a conversion for us. So it's 1.77 times 10 to the 13th meters. That has no place in our head. We just can't imagine a distance that big. So we'll just write it down, 1.77 times 10 to the 13th. The next thing we want to do is figure out how long it takes light to travel that distance. We got to find the time. So we're going to solve the distance equals the velocity for the times time for the time. And we are trying to figure out the time. We know the velocity is the speed of light, 3.0 times 10 to the 8th. So we take the distance divided by the velocity. This is meters per second. So our answer is going to be in seconds. And it turns out to be 59,000 seconds. So light traveling 186,000 miles every second will take 59,000 seconds to get all the way from Voyager back to Earth. To kind of help us get a handle on that, we don't really have a place in our brain for 59,000 seconds. So if we divide it by 60, that tells us minutes. Divide it by 60 again, and we get hours. Turns out it's about 16.4 hours. Okay? Now, as you solve the problems, be really careful. Make sure that you know what kind of problem you're solving. For example, if I said, how long would it take for a signal to go from Earth out to Voyager and then back, the distance would be 2 times the distance to Voyager. So just when you're doing a problem that involves a round trip, so sending a signal from Earth to the moon and comes back, remember that the distance it's going is twice the distance from the Earth to the moon, for example. Okay, so if I said, how long does it take to communicate with Voyager and receive an answer? The answer is about 32.8 hours. But remember, that's the time it takes the signal to go there and back. There's several problems in the homework where you will get the wrong answer if you don't consider whether you're dealing with a round trip time or a one-way time. Okay, so you've got some problems to solve. Good luck. Holler if you need help.